We've all looked up at the stars at night and wondered about them. But can you imagine what it would feel like if you looked up at the stars and you saw nothing, no stars at all? Well, that's what it was like for about 200 million years after the Big Bang. As the universe expanded, it got colder and colder and darker, and frankly less and less like a place that might produce things like you and me. Astronomers call this part of the universe's history the Dark Ages. During the Dark Ages, you had a lot of atoms flowing through space. You had about 75% of them were hydrogen with 1 proton. About 25%, most of the rest, were helium with 2 protons. And there was a tiny sprinkling of beryllium, of lithium. Lithium's got 3, beryllium's got 4 protons, and finally of boron. The whole universe was really very, very simple. Everywhere you looked, you seemed to have the same temperature, the same density, the same types of atoms. Really, everything was uniform. And that's a real problem, because it seems as if the universe was just too simple, too uniform for anything interesting to happen. How could you produce you and me from such a universe? More complex things seem to appear when you have just the right Goldilocks conditions for their appearance. So what were the perfect Goldilocks conditions for creating just a bit more complexity in the early universe? Well, it turns out that those conditions were scattered all through the universe. The crucial things you needed were, first, lots of matter, secondly, gravity, and third, tiny differences in the distribution of that matter. And they were all there. There are some areas that are just slightly hotter and slightly denser than others. In those areas, gravity was just slightly more powerful. So what it did was it clumped those areas together. As they clumped together, they got denser, so the power of gravity increased, and they began to clump even further together. Gravity increases, so the whole thing is clumping a bit like a runaway train, and this gets faster and faster and faster. And now what happens is at the center of each of those clouds of atoms, atoms begin to bang into each other really violently, and they begin to heat up. Eventually, the temperature reaches about 3,000 degrees. The temperature in the cloud keeps rising until eventually it reaches 10 million degrees. And something spectacular happens at that temperature. Protons start banging together so violently that they overcome the repulsion of their positive charges and they fuse together and are now held together by the strong nuclear force. As that happens, there's a huge release of energy as some of their matter is turned into pure energy. This is very similar to what happens in an H-bomb. So now, at the center of the cloud, we have a sort of furnace that's pushing back against the force of gravity and that stabilizes the whole thing. And now what's happened is a star has lit up. We've now crossed our second major threshold of complexity in this course. From about 200 million years after the Big Bang, the universe starts filling up with stars, billions and billions and billions of them. And the universe is now a much more interesting place. Stars increase the complexity of the universe in another way. They gave it new types of structure at many different scales, from the level of the stars themselves, to galaxies, to superclusters. Let's begin with the stars. Stars themselves have a very clear structure. At the center, you've got protons that are at an extremely high temperature, as we've seen, and they're fusing to form helium nuclei. Just around the center, around the core, you have a sort of store of protons ready to be fused eventually when they sink down into the center. Now, photons of energy and light from the center slowly work their way through the plasma, taking sometimes thousands of years, until eventually they reach the surface and then they flash out into space. But stars themselves are gathered together by gravity into much larger structure. We call these galaxies. Our Milky Way is our galaxy. It contains perhaps 100 billion, some say 200 billion stars. It's absolutely huge. And there may be 100 billion galaxies in the entire universe. But structures exist at even larger scales too. Gravity gathers galaxies together into what are called clusters. Our local group is a cluster like that. It contains about 30 galaxies, including Andromeda and the Magellanic Clouds, both of which you can see with the naked eye. Gravity can even hold clusters together to form what are called superclusters. These scatter through the universe in huge webs and sort of chains. But beyond that, gravity is too weak to hold superclusters together. And it's beyond the level of superclusters that you begin to see finally what Hubble saw. You see whole superclusters moving apart, and there, at that scale, you can see the expansion of the universe.